In this video, we're doing de Moivre's theorem, higher level only. And the fastest way to see why it's worth having is to watch the same question done both ways. Work out 1 plus I to the power 8. On the left, the binomial expansion. 9 terms, and every single one of them has a power of I in it that needs cleaning up. On the right, de Moivre. 1 plus I is root 2 cis pi over 4. Raise root 2 to the 8th, that's 16. Multiply pi over 4 by 8, that's 2 pi. 16 cis 2 pi. And a full turn brings you back to where you started, so that is just 16. 2 lines. That's de Moivre's theorem, and this video is what it says, and the 2 things it is really for. So here it is. R cis theta all to the power n is r to the n cis n theta. Raise the modulus to the power and multiply the argument by it. And that should look familiar from last video. Multiplying added the arguments. So multiplying a number by itself n times adds the argument n times. And adding something n times is multiplying it by n. De Moivre is not a new rule. It is the last one, applied repeatedly. And it holds for any n. Positive whole numbers, negative ones, and fractions. That last case is the one that does something genuinely new, because a fractional power means a root. And that is where de Moivre stops being a shortcut and starts telling you things you could not otherwise get. Example 1, the one from the opening. 1 plus I to the power 8. Convert first. The modulus of 1 plus I is root 2. The argument is pi over 4. So 1 plus I is root 2 cis pi over 4. Now de Moivre. Root 2 to the 8th. Cis 8 times pi over 4. Root 2 to the 8th is 2 to the 4th, which is 16. And 8 times pi over 4 is 2 pi. 16 cis 2 pi. 2 pi is a full turn, so it lands straight back on the positive real axis. Cis 2 pi is 1. The answer is 16, and you can check that without polar form at all. 1 plus I squared is 2i. So 1 plus I to the 4th is 2i squared, which is minus 4. And minus 4 squared is 16. Same answer. Example 2. Straight application. No conversion needed. 2 cis pi over 6 all to the power 5. Raise the modulus. 2 to the 5th is 32. Multiply the argument. 5 times pi over 6 is 5 pi over 6. 32 cis 5 pi over 6. That is it. That is the whole method when the number is already in polar form. Example 3, a negative power. 1 plus I root 3 to the power minus 3. Convert first. The modulus is root of 1 plus 3, which is 2. The argument is pi over 3. So it is 2 cis pi over 3. Now de Moivre with n equals minus 3. 2 to the minus 3, cis minus 3 times pi over 3. 2 to the minus 3 is 1/8. And minus 3 times pi over 3 is minus pi. 1/8 cis minus pi. Cis minus pi is minus 1, so the answer is minus 1/8. And notice, a negative power gave a purely real answer. Nothing has gone wrong. The rotation just landed exactly on the negative real axis. Example 4. And this is the part de Moivre is really for. Find all 3 cube roots of 8. Now, real numbers give you one obvious answer, 2, because 2 cubed is 8. But there are 3. Here's the trick, and it is the only genuinely new idea in this video. Write 8 in polar form, but write the angle generally. 8 is 8 cis 0, but it is also 8 cis 2 pi, and 8 cis 4 pi. Adding a whole turn does not move the point, so write it as 8 cis 0 plus 2 pi k for any whole number k. Now take the cube root. A to the 1/3 cis 0 plus 2 pi k all over 3. A to the 1/3 is 2, so it is 2 cis 2 pi k over 3. Now just put k equals 0, 1, and 2. K equals 0 gives 2 cis 0, which is 2, the obvious one. K equals 1 gives 2 cis 2 pi over 3. Cos of 2 pi over 3 is minus a half, and sine is root 3 over 2. So that is minus 1 plus I root 3. K equals 2 gives 2 cis 4 pi over 3, which is minus 1 minus I root 3. And k equals 3 would give 2 cis 2 pi, which is 2 again. You are back around the circle, so stop. Let's check the middle one. The modulus of minus 1 plus I root 3 is 2, and its argument is 2 pi over 3. Cube it. 2 cubed is 8, and 3 times 2 pi over 3 is 2 pi. 8 cis 2 pi is 8. It works. And here is the pattern worth remembering. There are always exactly n-nth roots. They all have the same modulus, r to the 1 over n, so they all sit on one circle. And they are spaced evenly round it, 2 pi over n apart. 3 cube roots means 3 points, 120 degrees apart. Sketch the circle, mark the first root, and you can place the rest without computing any of them. And this is worth saying plainly. Ask a calculator for the cube root of 8, and it gives you 2. One answer. It will not give you the other 2, and it will not tell you they exist. De Moivre does. Example 5. And this is the second thing de Moivre is for. Show that cos 3 theta is 4 cos cube theta minus 3 cos theta. By de Moivre, cos theta plus I sine theta, all cubed, is cos 3 theta plus I sine 3 theta. Now expand the left-hand side with the binomial theorem. Cos cubed theta plus 3 cos squared theta times I sine theta plus 3 cos theta times I sine theta squared plus I sine theta cubed. Clean up the powers of I, and that becomes cos cubed theta plus 3i cos squared theta sine theta minus 3 cos theta sine squared theta minus I sine cubed theta. Now the key move. Those two expressions are equal, so their real parts are equal, and their imaginary parts are equal. Equate the real parts. Cos 3 theta equals cos cubed theta minus 3 cos theta sine squared theta. Nearly there. Replace sine squared theta with 1 minus cos squared theta. That gives cos cubed theta minus 3 cos theta plus 3 cos cubed theta. Collect. 4 cos cubed theta minus 3 cos theta. Done. And you got a second identity for free. Equate the imaginary parts instead, and you get sine 3 theta equals 3 cos squared theta sine theta minus sine cubed theta. One expansion, two identities. Raise the modulus, multiply the argument. And when the power is a fraction, you get every root at once, sitting evenly spaced on a circle. That is the end of the complex numbers block. Next video is still higher level. Proof by induction.